Now, if you have 10 gigabytes of data, put everything in a multi-regional bucket and don't worry about it. Why do I say that? It doesn't cost you anything anyway. But if you have many terabytes, petabytes of data, all of a sudden the storage cost is going to start adding up pretty quickly. And that's where you really should understand that, right? But anyway, that's create the bucket, specify the class and the location, and hit create, you're good to go, okay? I guess other features of storage, so again, a lot like S3 storage, you can set up lifecycle rules, that's super easy. You can have like event notifications. If an object ends up in the bucket, kick off a cloud function to process the data, things like that. You can turn versioning on if you want to. If you turn versioning on and you overwrite a file inside the bucket, it'll keep the old file under a different name. You don't pay extra for that other than you pay for the storage of the older versions and so on, okay? Go ahead and switch back to the slides. Okay, again, so specify storage class and location. You have complete control over who can access the bucket or the objects in the bucket, so you use IAM for that. Again, you turn versioning on and lifecycle management and so on. Again, cloud storage is blob storage. There's no limit to the amount of data you can put in a bucket. There's no limit to the number of files you can put in a bucket. The maximum size of a single object is 5 terabytes in storage. You don't have to turn encryption on. Encryption is on by default. You can, if you want to, manage your own encryption keys, but Google doesn't, they give you that choice. If you have to conform to a compliance standard or some regulation which forces you to manage the keys, you can do that. If that is not the case, you can let Google manage the keys for you. All right? Again, we already talked about the 4 storage classes. Anyway, that's cloud storage. Super easy. Okay? And then Bigtable. Bigtable is what is known as a wide column NoSQL database. It is similar to something like Cassandra or HBase with big. Go ahead and switch back to the demo machine for me. If I want to use Bigtable, there's a service called Bigtable. First thing I have to do is create essentially the servers, if you will, like a Bigtable instance. We got to give that a name. Oops. Did I spell that right? That's spelled right. Give your instance a name, and then scrolling down here, this is just choosing, do I want to store the data on SSD drives or regular magnetic drives? What would you guess is the advantage of an SSD drive? It's much faster. What would you imagine the advantage of a magnetic drive is? It's much cheaper, right? So again, it depends on what is your application? What are your application requirements? What are your storage requirements? But anyway, pick a storage type. Scroll down a little further. Pick a zone to run your Bigtable database in. The number of nodes, right? Number of nodes essentially is the number of processing nodes processing the data for Bigtable, right? So with Bigtable, you don't scale by making the database instances bigger, you scale by adding additional nodes. What they tell you is for a production database, you should have at least 3 nodes. So we can add 3 nodes. If we want to, we could add clusters and additional zones, right, if we needed to do that. But anyway, you're creating the database, just fill in the form. When you're done filling in the form, hit create. That'll spin up the Bigtable database for you. Once you have the database, then the coding is super easy. In Bigtable, you create tables. Tables have rows. Every row in a Bigtable table has to have a unique identifier, which identifies that row. Associated with that ID can be any number of columns. You can put any kind of data you want to in an individual column. So you can put like simple data like a string or a number, or more complex data like an HTML file or a JSON string or an XML string, whatever you want. It doesn't matter. You put whatever you want to in a column. The rows in the table don't have to have the same columns. Does that make sense? Like one row could have 10 columns, the next row can have 20 columns. It doesn't matter, right? You can have sparse data or whatever. There's no schema that defines what a table looks like. It's just a table has IDs and IDs have columns, right? As long as you're searching a table based on the ID, it'll give you that data back at lightning speed. If you have to search through the columns, what do you suppose you have to do? Yeah, if you have to find data based on a column value, there's no way to create an index, so you have to do a full table scan, right? So I guess if you're storing data in big table, the key is to define how you're going to, or to figure out how you're going to define that primary key to most efficiently be able to select the data from the table. Underlying in storage, the data in a table is divided into multiple pieces that they call tablets. Tablets are stored in alphabetical order based on the row key. So that's your only index. Why do you suppose they don't support lots of indexes in Bigtable? Indexes slow everything down. Bigtable is designed for super fast writes. Does that make sense? If you have a database that supports lots of indexes, every time you add a row, you have to do what? You have to stop and update all the indexes. Well, Google accumulates data at such a fantastic rate, they can't stop and wait around for all the indexes to be updated, so they always support one index. That's the key, right? The order in which the data is stored. Right? But anyway, it's Bigtable. Yeah? If you want a NoSQL database, and especially if you're accumulating data very quickly, Bigtable is a good solution. If you're migrating from, say, an HBase internal system into GCP, Bigtable is a good solution. Bigtable uses the same API as HBase does. Like if you had a bunch of Java code that read from an HBase database, all that code would work for Bigtable. You just have to point it at a different source. Yeah? If you're using, say, Cassandra or something like that, and you don't want to manage the databases, then Bigtable may be a good alternative for you. Okay? Go ahead and switch back to the cloud. Yeah, Bigtable is managed NoSQL. I guess that's the other cool thing. It is more or less completely managed for you. All you really have to specify is number of nodes and where you want to put it, and then Google takes care of all the rest. So again, they take care of backing up the data or replicating the data. Like all storage choices, everything is encrypted. And of course, we can control access to Bigtable. And Bigtable is a very proven product. Lots of internal Google applications use Bigtable as their underlying storage mechanism. Again, lots of use cases for Bigtable. Let's say you're doing some sort of IoT type thing. Like imagine you're a manufacturer and you want to put sensors in all the machinery on the manufacturing floor. And every second you want every sensor to take a reading. And you need some place to put that data, and there's going to be a lot of it coming in. Then Bigtable would be a good solution for that sort of use case. If you were, say you're an online game company and you produce a game that goes viral, and now you want to track every move, but you need a place to put the moves from the millions of players who are playing simultaneously, Bigtable might be a good solution for that type of thing as well. Anytime you're streaming in lots and lots of data, Bigtable might be a good use case or a good storage thing for those use cases. All right? But anyway, Bigtable is NoSQL. Sometimes we don't want NoSQL. Sometimes we want relational storage, right? Like NoSQL is schemaless. Sometimes we want schemas on our data, like we want to define the tables and set up constraints and relationships and so on. That's where a relational database comes in. Sometimes we want lots of indexes, sometimes we want transactions and so on and so forth. So Google gives us two choices if we want relational systems. So go ahead and switch back to the computer. The first choice is called Cloud SQL. So if we want relational database, go to Cloud SQL, hit create instance. You have two choices for databases, MySQL and PostgreSQL. Let's say we want MySQL. So then we'll just run the wizard and create the MySQL database. We'll call this one Oshi. Generate a password. You got to log in once. Any relational database people here? Cheer as loud as you can if you're a relational database person. Woo! Okay. Look, it's just MySQL. So I'm going to create a database. The first time I'll log in as root. Once I log in the first time, then I can create users and passwords and then disable root. All right? I got to put my NoSQL database somewhere. So let's say we put it in US East 4 and we pick Zone A. And then there's some advanced configuration options down below. How big a machine do I want? I guess it depends on how many users do I have, how much data do I have. So I can have a very small machine, or I can create a very large machine. In the end, you are creating a virtual machine behind the scenes. Do I want to store it faster on SSD drives, or do I want to store it cheaper on spinning drives? I guess it depends on the app. And then how big of storage do I want? Remember, in the cloud, you should always start small, and when you need more, then it's easy to make things bigger, right? So the minimum size of storage is 10 gigabytes. The maximum size is about 10 terabytes, yeah? Start small, check this box, and it'll make storage grow as you start running out of space. It'll do backups automatically for you, so just leave the backups on if it's a production system. Also, there's a little checkbox right here. If you check that box, it'll create an exact duplicate of your Cloud SQL database in another zone for high availability. Remember, if you want high availability and fault tolerance, you have to have at least two of everything, and they have to be in different zones. So that's exactly what it does. So I think we picked US East 4A, it'll put another duplicate in another zone in US East 4. Make sense? So again, it depends, right? What do you suppose that does to your cost if you check that box? Multiply by what? By 2, right? But anyway, all you got to do is check the box and it'll take care of the work for you. As far as security goes, just note that when you create a Cloud SQL database, nothing can reach it outside of your project until you open it up, right? So it is secure by default. You can pick and choose from where we can access that database. You can control a maintenance schedule if you want to, and so on down the line. But anyway, configure the database, hit create, that will create the Cloud SQL database for you. From that moment on, it's just MySQL programming. There's absolutely nothing that you do in MySQL somewhere else that you can't do there, because that's all it is, right? They're very adamant about that. We didn't customize it to run on our platform, so if you're used to MySQL, you can just migrate code in and you don't have to worry about it not working for some reason. But anyway, that's Cloud SQL. The other relational system is called Spanner. So if I go here to Spanner and I say I want to create an instance, it's kind of the same thing. I'm going to fill in a form, and then I'm going to create the Spanner database. Now, with Cloud SQL and with most relational database systems, if our application or our database starts to get really, really busy and it can't keep up with the demand, usually what we want to do is scale up. Scaling up means Add CPUs, add memory, add storage. Are you with me? With Spanner, you don't scale up, you scale out. So you scale by adding additional machines, not by making the machines bigger. Now the trick is, there's two consistency models that are common with relational systems. One is called eventual consistency, and another one is called strong consistency. With eventual consistency, I might have multiple copies of the data, and someone comes along and they change a record. That record will get changed in one of the copies, and then asynchronously, eventually, all the other copies will get synchronized to match the change. But when you're using an eventual consistency model, it's possible that, like, I went in and changed a record, but you come in right behind me and ask for the same record. If you get it from a different copy and they haven't been synchronized, you may not get the latest and greatest version of the data. Does that make sense? There are lots of use cases where eventual consistency is perfectly acceptable. Can you think of one? Let's say you're doing product reviews on a website. I come in and I add a product review, and you come in right behind me and say, show me the reviews for this product. My review doesn't show up. If you were to come by 100 milliseconds later, you'd have seen my product review. But you got unlucky and you didn't see it. Is the world going to come to an end because you didn't see my product review? It doesn't matter, right? Hit refresh and it'll be there. There are other use cases where it is not acceptable, or where eventual consistency is not acceptable. Give me one of those. Like a banking sort of operation. Or maybe I change the price of the product. If I change the price of the product, I want it to be changed, period. Yeah? So in that case, eventual consistency is not going to work. Usually with systems that scale out by adding multiple copies, usually those types of systems support eventual consistency. Spanner is a relational system that scales by adding multiple nodes, but it supports strong consistency. And that's the trick, and that's what's hard to achieve. Also, Spanner is unique because not only can you scale it, not only can you scale out, but you can scale out to multiple regions or multiple parts of the world at the same time. If you notice here, like I'm going to create an instance, and then there's a configuration here, and then I got two choices, regional or multi-regional. So if I pick regional, maybe I'll pick US Central 1. Now, no matter how many nodes I specify down here, 1 or 10 or 100 or 1,000, in that case it would all be in US Central 1. But if I pick multi-regional, then I can pick either North America 3, meaning we're going to deploy nodes to 3 data centers in North America, or if I have customers all over the world, I can deploy it to North America, Europe, and Asia, all at the same time, and I can have any number of nodes, right, down here, like 3 or 30 or 300 or 3,000, and then once I fill in those couple questions, when I want my Spanner database, all I got to do is click here, create. Yeah? Now let's talk about cost for a minute. Let's say we want to deploy a Spanner database all over the world, and I have 50 terabytes of data that I have to manage. Now, what they tell you is a single node can manage about 2 terabytes of data. So let's say I had 50 terabytes of relational data, and I want to deploy it all over the world. If it's 50 terabytes and I need 1 node per 2 terabytes, now I need how many nodes? 25, right? Let's open up the price calculator. Google Cloud Price Calculator. Is that it? Oh, that's not it. price calculator right here. Let's pick spanner, 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 spanner. Let me know if you see it. There it is, spanner. It's our database. I'm going to pick multiple regions all over the world, 25 nodes. We're picking 25 nodes because we have 50 terabytes of storage. Add that to our estimate. We'll slide this over to a year, and that'll cost us a mere $2.5 million. That's an unbelievable deal, right? Now look, here's the thing. Everybody laughs, but once in a while, a guy in the room will be like, oh, I'm trying to keep like multiple Oracle enterprise databases synchronized in my own data centers around the world. When that guy sees $2.5 million, what do you suppose he does? He gasps even louder than all the other people gasp, but not because it's expensive, but because it's unbelievable. From his point of view, it's unbelievably cheap, and there's no licensing to pay either. It's just you give them $2.5 million and you have that database. It's really good. Yeah. But anyway, that's Spanner. So obviously, Spanner is not for everybody. It's for the right use case. But when the right use case comes along, it's a good solution. Go ahead and switch back to the slides. Anyway, so I guess the moral of the story is if you want to run a relational database, Cloud SQL or Spanner, and remember, Cloud SQL is either PostgreSQL or MySQL, okay? There's a second NoSQL database in Google Cloud called Data Store. Remember, like the first NoSQL database we talked about was Bigtable. Bigtable is super cool, but Bigtable is missing some features that a lot of people want. Number one, you can't create indexes in Bigtable. So you create tables and you can't index the data. Also, Bigtable does not support ACID transactions. Like you can't update multiple tables or multiple rows within a table in a single transaction. It's because Bigtable is designed for super high performance. In order to solve those couple problems, Google created a second NoSQL database called Data Store. Data Store is actually built on top of Bigtable. Right, so it's using like Bigtable as the underlying storage technology, but it hides a lot of that stuff for you. So if you want to use Google Cloud Data Store, you create a Data Store database. There's only one thing you have to tell it. What region do you want to put the database in? Magic happens, and about a minute later, you have a data store. Then you can start saving entities to the data store. Entities have properties. Properties have values. By default, all properties are indexed. You can create secondary indexes to index multiple properties at the same time if you need to, and it'll just work. Data Store supports transactions, so that's cool as well, meaning I can update multiple entities in a single transaction. Everything succeeds or everything rolls back. So if you want a NoSQL database more along the lines of MongoDB or something like that, Data Store would be a good candidate for that. There's also a free tier in Data Store. You get 1 gigabyte of Data Store data free per month. So for a lot of smaller use cases, people don't even go beyond the free tier and they never get charged. Think like I'm storing product reviews, I'm storing user profiles, product information, stuff like that I'm integrating into, say, a web app. Data Store is ideal for those scenarios. Right? But anyway, Data Store and Bigtable are 2 NoSQL database choices, and then Cloud Storage, and then Cloud SQL and Cloud Spanner for relational storage. Okay? Okay. Now containers. Have you heard of those? Containers? How many people have heard of that? What's a container? Anybody ever hear of like Docker or something like that? Have you heard of Kubernetes? let's talk about containers and Kubernetes. Maybe we can do a little deployment. Okay. So a container is like a very lightweight virtualized package for deploying an application. I guess, look, we can buy a physical machine and we can install an operating system on the physical machine. We can create a we can buy a physical machine and then install some sort of virtualization software on that machine, like VMware, something like that. If we install VMware on a machine, now we can have multiple operating systems on the same machine. If I have multiple operating systems on the same machine, I take greater advantage of the hardware. But a virtual machine is big and it takes a while to boot. Like if I start a virtual machine, that'll take, I don't know, 30 seconds or a minute or a couple minutes, depending on the underlying computer. A container sits on top of a virtual machine. I guess it could be a virtual machine or a physical machine. But a container starts and stops very, very quickly because a container makes use of some of the underlying services on the operating system. Right? So containers are smaller than virtual machines. Since they're smaller, you can move things around quicker. They start really, really fast. A container will start in like a second, where a virtual machine takes like a minute to start, something like that. Containers give developers consistency, right? I remember when I was a young programmer, somebody said, oh, your test environment has to be the same as your production environment. And I sort of snickered at them, oh yeah, sure. What world do you live in? Right? But that used to be hard, but if our development environment, our test environment, our production environment are all in this container, then it's a lot easier. Maybe you can't get 100% there, but you can get pretty close to your development and your test environment, your production environment being pretty much the same things. So that makes like deployment more reliable and testing easier and so on. A container will run on any system that has like the container software installed on it. Like if I put my application in Docker, now I can run that application on any machine or any virtual machine that has Docker installed. Right? And the other thing, like to me, the best part of a container is when I deploy one app on a machine and then another app on the same machine, I'm not polluting the underlying operating system with requirements for each application. Like let's say I deploy an application on a machine with whatever .NET framework on it. And then later on I say, well, I'm going to deploy this other application with the .NET framework on it, but it's a different version of the framework. Now that's supposed to work just fine. How many people have ever installed a new thing, though, and broken an old thing? Has that ever happened to you? Well, it's not supposed to happen, but it does. But if everything specific to the application is in the container, then it's far less likely that's going to happen because the server running the container doesn't know what's inside. It didn't have to have Java installed or Python installed or .NET installed or whatever. It just has to have Docker installed, right? But anyway, so again, like containers are fast. And the most commonly used container is Docker. It's not the only one. Now, that brings us to a thing called, well, let's say we deploy our applications in containers. We have to have some way of managing the containers. Or to make our lives easier, we don't have to have a way of managing containers. We want to have a way of managing containers because it's going to make our lives easier in the long run. Docker has a thing called Swarm. Google, they have a thing called Borg. Google released Borg to the outside world, and they called it Kubernetes. Kubernetes is there to help you manage the deployment of your applications. Right? In the cloud, I want to deploy lots of little things. Remember we were talking about that earlier? I want to optimize things, so I don't want to have a small number of big things. I want to have lots and lots of little things. Why do I want lots of little things? I always want more than one thing for fault tolerance, and then I want to turn lots of little things on or off to scale up and down to meet demand. If my application has more than one instance, in front of the application, I always have to put what? load balancer, because the requests come into the load balancer, and then the load balancer forwards the request to one of the instances. And then if I want to scale up and down, then I need an auto scaler. So every application is going to have those three things. But I'm not putting one application on one machine. I want to put lots and lots of applications on machines. And essentially, I want to fill up the machines as much as possible, thereby taking greatest advantage of the underlying hardware that I'm paying for. The one thing I didn't understand about Kubernetes for the longest time was the why. Why do I want to do that? Like I'd be watching a demo or something, and a guy would pull up a Kubernetes configuration file, and I was like, oh my God, I don't want to do that. Why do I want to do that? Why do you want to make your life so hard? And then I realized one day, why? Why do we want to use Kubernetes? That's a real simple answer. It's all about the cache, right? So I want to buy as few machines as possible and pile as many applications into those machines as I can. I want to stuff applications into those machines. Sit on the lid and duct tape it. Yeah? That's what Kubernetes is. Kubernetes is all about saving money, right? Now I'll tell you what we'll do. Let's see if we can deploy something with Kubernetes. Okay? So let's go here to, hold on. Here's Kubernetes engine. Look, let's say I wanted to create a Kubernetes cluster. So I click on this link right here and I fill in the form. Right, so I give the cluster a name. I can have zonal or regional clusters. Like zonal means everything's in the same zone. Regional means we're going to use multiple zones within a region. We can specify how big, like a cluster is a collection of machines. We can specify how big machines we want. We can say how many machines we want down here. And then there's a whole slew of advanced options like auto-scaling the cluster and using preemptible instances and updating the clusters and so on and so forth. So I could go here, fill in the form, and hit create. I'm not going to do that, though. I want to script everything. Like this is a good way, like going into the UI is a good way of seeing what's available. That's not really what I want to use. Right? So let's go back. We want to create the clusters in a script. So, which I'm going to do down here. Let's, here, I'm going to reconnect there. Yeah, give us a second to reconnect. Okay, so we're connected here, and we're in this project called caps-win, and I'm going to cheat a little bit. I got some code that I already wrote, but we'll create a cluster, and then we'll deploy this code to the cluster. So there's a folder here, DevOps demo, and inside there's a folder called default, and inside here, it's just a little Python program, right? So if I wanted to run the program locally, I could just type Python space main.py, and hopefully that'll work. Oh, I'm sorry, I'm in the wrong folder. Let's try that again. Python space main.py. Hopefully that's going to run. So it says here that it's listening on the local machine via port 8080, and if we go here to web preview, we can preview that on port 8080. It says, hello, Caps fans. Everybody cheer, woo! So there's our little program that we're going to deploy. So now if we go, so now we see we can run it locally, so let's stop it there. Now, there's a business, when they started it started on port 8080. It's on port 8080 because you see where it says if name equals main, and I say app.run, notice I'm running it on what port, everybody? 88. Keep that in mind, right? Now, I want to take this program, if I want to put it in a Docker container, look, I got a little cheat sheet, right? That's not for demos. If I was doing a project in the real world, there'd be a text file called cheat sheet in the folder, right? I can't remember all this stuff. But anyway, if I want to take this program and I want to put it in a Docker container, I could run this command right here. So notice it's docker build -t, we're going to tag the machine, tag it like we're giving it a name, right? We're going to call it drems from / DevOps demo, :latest means it's the latest version, and then it's not a typo at the end, space period at the end. What do you suppose the space period means? What's a period mean in Linux? Yeah, the period means the current folder. So let's take that command and we'll put it down here. Whoops, sorry. I'm not used to Windows using the wrong keyboard shortcuts for copy and paste. How come they can't use the standard Command-C, Command-V? It's weird. But anyway, that's going to build a container. Now, space period means, in Docker, like it's saying, build the container, and then when you build a container in Docker, it looks for a file called Docker file. So my file called Docker file is in that current folder. That's the period. So the Docker file here just says, start with the Python container version 2 base load, or base container. This, where it says working directory, that's almost like CDing into that folder, but it's not on my machine, it's in the container. Does that make sense? Like set that as the working directory inside the container, and then this is, my app is a little Flask app, so I have one dependency, so it's Python, pip is Python installer program. So you just say install Flask within the container, yeah? And then this is a weird looking command here. Copy space, period, space, period. The insanity of the whole thing. That's saying period means the current folder, right? And then in the long run, and I'll save money in lots of different ways, but I'm trying to, I don't want like virtual machines that are vastly underutilized. I want to maximize the usage of those virtual machines as much as I can. But it still is work, and it requires coding, and it requires administration and monitoring. It's not like it's free and easy and a no-brainer, right? It's kind of hard to learn. Right? If you don't want to have to learn all that stuff, then we can use platform as a service. Right? In Google Cloud Platform, there is a thing called App Engine. App Engine was Google Cloud's first service. Google thought, like, what was that, about 8 years ago, like about 2008, 2009, I think App Engine was released. Google thought when people see App Engine, obviously they won't want to deploy their applications any other way, and everyone will start writing App Engine apps. Well, that didn't happen, right? There was, again, like an understanding of App Engine that people needed, and you can't just like pick up a running app and run it in App Engine. Your application has to be written in a way that supports App Engine. Now, that's not a huge deal, but it would, like if you were running an application within a data center, more than likely some changes would have to be made in order to write it as an App Engine, or run it as an App Engine application. But anyway, App Engine is their platform as a service. App Engine is the bomb. App Engine is super easy. It is easy to deploy your apps. It's easy to maintain your apps. It's massively, massively scalable, right? Like, it takes care of all that work for you. It creates a load balancer for you. You don't even have to know the load balancer is there. It creates the autoscaler for you. You don't have to do any of that. It's just all magic behind the scenes. Every request to an App Engine application gets sent into a queue before it gets sent to one of the instances. Right? So if the instances get really busy and they need to scale, you don't lose a message because the messages are waiting. Okay, now I'm ready to collect the message. I can grab it real quick. So again, it's super easy and super automated. It's especially useful for building scalable web applications. Now, in my little world, every app, other than a database, I guess, every app should be a web app in my little world. I've been a web developer since 1995. How long ago is that? I don't know why I'm not retired. But that's ridiculous. Every app should be a web app, dude. That's the way the whole world runs on the web. Right, and by web app, I mean a web application or a web service. But if you want to do a back-end service, expose it as a web service. What's the difference between a web service and a web application? Nothing. Like a web application, you make a request to an endpoint and it returns HTML. If you want to create a web service, you make a request to an endpoint and it returns what? JSON. What's the difference between HTML and JSON? Nothing. They're strings. That's the beauty of a web app. Make a request, return a string. Right? App Engine is designed for those types of applications. App Engine is designed for microservice type of architecture. When you create a project, there's one App Engine application per project, but that application can consist of any number of underlying services. Collectively, the services make up the whole app. That's kind of what like a microservice type of deployment is designed to be. Okay? There are two environments that you can use with App Engine. One is called standard environment and one is called flexible environment. Notice they didn't call them legacy environment and new environment. It's standard and flexible because, and I think they're very careful with the naming. Standard environment is older, but that doesn't mean it should not be used. It's like, if they didn't want you to use it anymore, they would call it legacy or classic or some awful thing like that. I'm telling you, there's a standard environment and the flexible environment. Like if I was going to draw like a decision tree, I say, I want to deploy an application on Google Cloud. My first choice would be App Engine Standard. And I would always use App Engine Standard unless there was a good reason that I couldn't. Then if there's a good reason that I can't, then maybe I would choose App Engine Flex, or maybe I would choose Kubernetes Engine. And if neither one of those would work, then I'd probably pick what? Compute Engine on a VM. I can get anything to work on a VM, right? But my number one choice would always be App Engine Standard. Now, why App Engine Standard? App Engine Standard, when you deploy your application gets deployed into a container, but it's not a Docker container. It's a Google-made container that's optimized to run on Google Cloud within App Engine. A Google container running an App Engine app will scale in about 200 milliseconds. Did you hear what I said? It'll scale in about 200 milliseconds. If your application will scale in 200 milliseconds, that means you can scale all the way to zero. When an App Engine Standard app has no requests, that's exactly what it does. It scales to zero. When it scales to zero, guess how much it's costing me to have that app deployed? Zero. But if a request comes in, guess what happens? Because it can turn itself on so fast, it'll serve up that request in like a second. It's like it was never turned off. This is cool in many different ways. If you're deploying a small app, like every company has those small internal apps that don't necessarily have a lot of users, but that doesn't mean they're not important. For those types of applications, when you deploy them to App Engine Standard, you may never go beyond the free tier and you may never get a bill. When you combine that with Data Store, which has a gigabyte of free storage, again, for small applications, you may never get charged. But the same application that you can deploy to 5 users can scale to millions of users. Think Snapchat. How many people use Snapchat? How many people's 12-year-old kids use Snapchat? Snapchat is an App Engine app, right? I'm sure they didn't think this thing was going to go viral, right? But when Snapchat was first deployed, how many users did they have? I don't know how many people programmed it. There were 2 users, but then it went viral, and now like every middle school kid in America uses Snapchat. They don't have an infrastructure team at Snap. They didn't have to re-architect the app to get scale from a couple people to millions and millions of users. The reason they didn't have to scale, or the reason they have to re-architect it to scale to millions is because they were running on App Engine, and App Engine is designed to run at whose scale? Google scale. Google has 7 applications with over 1 billion users. So your piddly little million-user app is just a blip, right, somewhere. It's nothing, yeah? This App Engine is so cool. Now, there are some limitations with App Engine Standard. App Engine Standard only supports 4 languages: Java, Python, PHP, and Go. For the life of me, I don't know why, if you give me Python, why do I need the other 3? It doesn't make any sense. But look, that being said, if you want to write your program in C#, okay, I'm cool with C#, but you can't do what? If you want to write in C#, you can't deploy it to App Engine Standard, because App Engine Standard doesn't support that language. And there's some other limitations as well. But like I said, I think somebody in the talk at lunchtime said, when you pick a deployment platform, it's not an all or nothing decision. Like if you're deploying an application with a microservice architecture, it's multiple applications. So for the ones that work with App Engine Standard, use App Engine Standard. If one doesn't work with App Engine Standard, then use something else, right? Again, you can pick and choose the best deployment platform for the scenario you're working on. There are a slew of other services that are associated with an App Engine app. Memcache for caching in memory, a little bit like Redis. There's a queuing system called task queues. If you want to send messages between different microservices, you can use task queues to do that. Like SQS for you Amazon people. It's very easy to schedule batch processing jobs. That's another really good use case for App Engine. Like I want to run some batch job in the middle of the night every night. App Engine is good at that sort of thing. There's a search system, logging, and so on. Now App Engine Flex runs in Docker containers. Any application I can get into a Docker container, I can deploy to App Engine Flex. Are you with me? And the code is super easy. Like, we saw the code to create a Docker container. Remember that guy? If you put your app in a Docker container, then deploy to App Engine, you just say gcloud app deploy, and then it deploys into App Engine. And it looks at a very small configuration file. You know how that Kubernetes configuration file was like that big? The App Engine configuration file is like this big, right? Like 3 lines of code. This is what I want, deploy it. This is kind of cool. But anyway, that's App Engine Standard and App Engine Flex. And then these slides are a little bit out of order. No. But anyway, those are your 2 choices for platform as a service. Again, there are pros and cons of each. Don't just think like one is better than the other. Use the one that is appropriate for the service that you're deploying. And again, to me, like the biggest difference is that first line. Instance startup, like when you scale with App Engine Standard, new instances start in milliseconds. When you scale in flexible environment, there's a one-to-one relationship between the Docker container and a virtual machine. So it scales at the speed of a virtual machine, which is also pretty fast, but it's not fast enough to scale to 0. So there's like no free tier with App Engine Flex. That's scaling to 0, like look, well, so cool. Anyway, now, if you're deploying have you heard of that term microservices? Have you heard of that? Look, the idea of a microservice is we used to have like one great big application and one code base. And then somebody said, well, as the code base gets bigger and bigger and bigger, it becomes harder to manage. And then sometimes we end up having lots and lots of people working on the same code base. The more people you have on the same code base, the more complicated everything gets. And then when we want to do things like deploy a new version, then we have to coordinate all the people working on all the different pieces of the application. This is not a problem if you have 6 people working on your company's website, but this is a problem when you have very large applications that you want to deploy. So one of the solutions to that is to divide the great big app into a bunch of different smaller apps. And then what you can do is like you can take teams of people and you say, look, you people over here, you're going to work on this service, and you guys are going to work on this service, and you guys are going to work on this service over here. So then each service becomes programmed individually. Each service is deployed individually. Each service is versioned independently of all the other services. So like, let's say I have a team and I'm working on a service. If I get a new version done, I should be able to deploy it when it's finished. I shouldn't have to coordinate with everybody else when I want to deploy my new service. Does that make sense? If my team wants to write our service in Python, and your team wants to write your service in Java, it should work, right? Because the services will talk to one another via what? HTTP. And they'll pass data back and forth in what format? JSON. Simple, right? Simple. But now I got all these different services to manage, and I have all these interdependencies to manage. And if I got to be pretty careful. If I deploy a new version of a service, I got to make sure I don't do what? I don't want to break anybody else. I certainly can't change the URL that everybody is calling. And there's also another weird complication. There are certain things that all services have to do, and I don't want to repeat myself over and over again. Can you think of an example of something that all services need to do? Authentication and authorization is probably the most obvious example there. So in microservice theory, the way you get around this sort of management is building something called an API gateway. An API gateway is the place everybody makes requests into, and then the gateway figures out where those requests are supposed to go, right, and point them at the right service. Does that make sense? It's like a layer of indirection between the clients and the back-end services. There's an old architect saying, there's no problem that can't be made more expensive with another layer of indirection. Yeah? There are two ways to create that API gateway in Google Cloud. One is with a service called Cloud Endpoints. Cloud Endpoints uses an open source framework, or is based on an open source framework called Swagger. You may or may not, if you're a programmer and you work on services, you may have heard of that. So Cloud Endpoints is one way of doing it. There's also another product called Apogee. Apogee has some features that Cloud Endpoints doesn't have. For example, with Apogee, you could have the standard and the premium version of the service. If a customer wants to use the standard version, you could throttle them to, say, 10 requests per minute. But then if they're willing to pay for the premium version, maybe you throttle them at 1,000 requests per minute. But you have to be able to sort that sort of thing out, and that type of programming becomes more difficult. Apogee will help you do that. Apogee will help you count the number of requests to a service per customer so you can charge them back. So if you have simple needs, like architecturally my application is pretty straightforward, build your API gateway with Cloud Endpoints. If you have a more complex scenario and you want to charge people and you want to have multiple customers and you want to do service throttling, things like that, then Apogee might be a better choice for you. Okay. All right. That brings us to another Q&A. Everybody, clap for the Googlers who are going to come up here.